The power method for iteration is probably the easiest to learn and the easiest to prove convergence. There's an older name that's often encountered, that of Stodola. This method was used back in the decade of 1910s on turbine blades. Those were steam turbines at the time rather than the conventional gas turbines of today. I like to give a geometric interpretation of the eigenvalue problem. You can see how matrices tend to rotate and shrink or elongate a given trial vector. Then that works into the so-called eigenproblem, where you find certain characteristic directions that have a special property. The power method and its convergence are then explained. Two enhancements are shifting and sweeping. And finally, we'll have some problems in a problem session. Before the era of computers, it was important to find simple methods that could solve vibration problems, and it was possible at that time to measure flexibility coefficients. So one of the early researchers in vibration was Stodola, and he found a way that he could do a solution by iteration. In this way, you do a number of forward multiplications. This would have been easier, of course, with modern calculating tools, but they probably had primitive adding machines at the time, so they could do the cumulative multiplies that were needed. Stodola found that with the measured flexibility coefficients, you could get the fundamental frequency of vibrating turbine blades in a steam turbine. The general eigenvalue problem that we like to work with is given here. But in Stodola's method, the rule is that you have some kind of a matrix, say the combination that I'm showing here, acting on a vector, which then creates a vector that lies in the same direction but with a coefficient modifying the amplitude. Now, the measured flexibilities actually correspond to the inverse of the stiffness matrix. Doing that inversion is a little bit tricky because it's nearly singular, but they were able to measure those flexibilities directly, in which case then you could form the CM pair of matrices. Now, interestingly, that's not a symmetric final matrix A, but it does converge nicely when you do the iteration. The process moves from left to right, that you put an assumed value of a displacement field there, and this would be the envelope of the vibration of the body, and then you get an improved value for that assumed vibration field on the right. Stodola's approach has been recast in more modern forms now. It's actually related to both the power method and the inverse power method if you look at them in certain ways. But we'll use the more modern discussion now, calling those methods the power and the inverse power method. And we'll concentrate on the power method in this lecture. Before going into the formal methods and their proofs of convergence, though, I'd like to give a geometric interpretation of what the eigenvalue problem is. A person often has a known matrix A and then would like to see how that matrix acts upon some arbitrary vector U. I might call that a trial vector in our discussion. Generally, the operation AU will rotate and either stretch or compress the length of the vector. So a rotation and a stretching is sort of the general idea. But the question is there a special direction, and I'll call that direction phi, and that will be used from now on to specify a particular characteristic direction, such that A times phi will give you back a stretch factor and the vector phi again. In other words, the product A phi is collinear with phi. Now that particular direction is called an eigenvector, and the stretching factor is the eigenvalue. This stretch could either be less than 1 or greater than 1, and there are some problems where it's negative. The basic problem that we describe in Stodola's method would typically at the outset have all positive eigenvalues, but we're going to do a shift in a few minutes that will create a situation where you actually get some negative eigenvalues. The physical system itself often has positive eigenvalues when posed in the nicest way. An interesting thing is that in an n-dimensional space there are not just one such characteristic dimensions, but there are often n such directions. Now I'm showing an example in a two-dimensional space where the horizontal axis, for instance, might be u1, the vertical axis might be u2. But in general, in n dimensions, then, you would have many such eigenvectors and corresponding eigenvalues. For simple problems, the other eigenvectors are often perpendicular in the Euclidean sense, namely a right angle here. But that's not true for the general eigenvalue problem, so I don't want to overemphasize that at this point. Let's look at a numerical example of an eigenvalue problem. We'll do it in 2 dimensions. Here I take a matrix which is known, and then the question is whether there's an arbitrary trial vector here which will have the nice property that when operated on by A, it's stretched and then turned into a replica of itself. If you normalize these eigenvectors with some rule, and there are typically 3 such rules, then putting the same vector on either side of the equation gives you a rather scaled problem such that this lambda has some physical meaning. It's kind of interesting that you have been given the matrix here, but you don't know a priori what the 2 components of u1 and u2 are, nor the lambda value. It will turn out that for real symmetric matrices, though, the amount of information given and then the information desired balances out, such that in this case, for a real symmetric matrix, we really have 3 independent coefficients here, and we're being asked to find 3 numbers. The 2 displacement amplitudes and then the stretching factor. Now in this particular case, it has been worked out by classical means such as a determinant solution. We're going to use iteration in this lecture, but the exact answers are unity and 6 for the stretch ratios or the eigenvalues. And then the eigenvectors, or those characteristic directions, are given here. In the smaller of the eigenvalue case, you have a unit value along the u1 axis and then minus 1/2. I'm showing the unit vector here as if it had been originally some sort of unit value in length, let's just say on a circle, lying on a circle such as that. On the other hand, the second eigenvalue with a stretch ratio of 6 and the second eigenvector lie in the direction 1/2 and 1, and a vector that originally was a small one lying perhaps a trial vector on this direction would be amplified by a factor of 6. So that if you took a set of trial vectors lying on the unit circle with their tip on the unit circle but their tail lying at the origin, then they would be mapped into some kind of an elliptical shape that's suggested here by the dashed line. And indeed you get something like a set of principal directions here. Well, those are our eigenvector directions. Now let's look at the power method of solution. This is an iteration, and we'll carry it out in several steps. We'll propose that the matrix A multiplies a trial vector U. The superscript S in the parentheses reminds you of what iteration number you're on. We'll give the improved values on the right an index that's one higher than the trial value on the left. We'll start out with a 0 iterate, or an initial value, for the eigenvector of the 1, 1 vector. I'm trying to exercise all of the physical coordinates in the problem by not having zeros in this trial vector. There are other choices that many people prefer, such as taking the terms on the diagonal of the matrix or the inverse of the terms on the diagonal. But we'll use this rather simple approach. That number then is put into this side, and it's then operated on. 2 times 1 is 2 plus 2 gives you 4. 2 times 1 is 2 plus 5 gives you 7. Now you have an intermediate vector here. Sometimes I call it an unnormalized vector, and you're trying to make it equal to this quantity over here. Preferably, you'd like this equation to balance out and to have a strict equality on both sides. If we do that, one way to do it is to work on the left side and then factor out the largest number, giving unity in that component, and then you have 4/7 in the other component. At this point, I'd like you to think of this as an identity, that we want to know what terms over here match these terms over here, and that's pretty obvious that the first estimate of the eigenvalue is going to be 7, and the improved eigenvector is going to have these components. So on the right in this figure, I've shown the initial trial vector, which lay actually on a unit square with a largest component of 1 in both coordinates. And then the intermediate vector, which is really A times U, is the larger red vector and is roughly 7 times as big. That completed our first iteration, and we ended up with an estimate of the eigenvalue and an improved eigenvector. I'll copy those down here just for bookkeeping purposes. I consider this to be a normalized eigenvector. Now we'll reintroduce that into the left side of the eigenproblem, and then we'll do our second iteration. We're hoping for these new improved values on the right. In general, you'd like this vector to be mirrored exactly by 1 over here, but we will find, in fact, that the trial vector upon operation is still being rotated, so you don't get a perfect answer at this point. When you multiply the numbers out, you get 8/7 here, and then you get 2 times 1, which is 14/7, adds up to 22/7. Likewise, down below here, we get 43/7. We want to make this equal to the right side. The common way is to now factor out the largest component and reduce it to unity, and we say that that is a normalization with respect to the maximum component. Again, you should treat this as an identity and see that lambda 2 is 43/7 and that the vector has this value here. So I repeat those answers below. If you remember, the exact eigenvalue, the larger of the two, was 6. And so we already are within roughly 1% or 2 here, roughly 2% of the right eigenvalue. So we're coming along nicely. The picture helps us visualize what's happened. Our original trial vector U0 lay here. Then those unit normalized vectors, the next trial vectors, were normalized to lie this time on a square rather than the circle that I spoke about in one of our first figures. So it's quite common to use this unit normalization. And as your trial goes on, then the trial vector continues to migrate around the periphery of this square. Our U1 was an improved vector and was stretched out this distance, not quite as much as the original U0 was stretched. This was a factor of 7. Now we have stretched only a factor of 6.1. And then after normalization, we've brought down this vector U superscript 2, which is almost coincident with U superscript 1. So the direction is starting to converge pretty well. I'll just state the results for a third iteration without showing the calculation. And here you find that the eigenvalue is getting rather close to the exact value of 6, only off 2 parts out of 600. And here the eigenvector, after normalizing the largest component, is only off roughly 2 parts here in 500. So these are both becoming rather accurate. I've found with practice here that to get a number of significant figures that's quite precise, it takes some 20, 30 iterations on this particular problem. And I often give that as a homework assignment to say how many iterations will give you perhaps 6 significant figures and so on. Now, in this case, our eigenvalue has converged from above, and that information is not useful because the way that we have calculated our eigenvalue is rather crude. It only uses the information from the maximum coordinate magnitude in the problem. When you have multi-degree of freedom systems, that becomes even cruder. There is a way, however, using a Rayleigh quotient that takes information from all of the components of your eigenvector at its current stage of convergence, and that really is the best estimate of the eigenvalue. Rayleigh years ago showed then that the eigenvalue in this particular problem, the way we're doing it, should converge from below. And since the eigenvalue in this problem is the reciprocal of the frequency, that shows that frequencies are converging from above. And that makes sense because it means that a model of your system, and as you're trying these directions, contains a lot of potential deformations that require higher energy. And to get the lowest frequency, as we're trying right now, means that you've got to find the particular shape that is the mode shape for the fundamental mode. And any content of higher frequency modes will contaminate that solution and make the frequency estimation higher than it should be. Anyway, problem 1 in the problem session, we'll discuss that. The convergence proof for the power method is straightforward and doesn't take many steps. It's based on the idea that the matrix A that we're using is going to typically be real, symmetric, and positive definite. For such systems, there is a representation theorem that says that any vector in the space can be represented by using the eigenvectors for that problem as basis vectors, and then using some coefficients here, which I might call the participation coefficients, and then summing up these vectors to give you this arbitrary vector. And it has to do with the fact that these eigenvectors span the space involved, your n-dimensional space, and they point in all possible directions. Also, because they are orthogonal in a general sense, that means they're as different as possible, then you get a unique set of coefficients here. There's no two ways to do this. So it's a perfect vector basis. Now, what we intend to do then is, in our mind, imagine this trial vector is broken up into such a sum as shown up above. When you operate on that, let's let the matrix operator A move inside the series in that sum and then act directly on the basis vector. Now, we already have a rule for what happens here that comes from the fact that phi is an eigenvector. The special condition is that phi is an eigenvector, and therefore the product A phi will yield lambda phi. So I show that here under the summation, where previously it was A phi. Now for a specific eigenvector and eigenvalue pair, I get lambda I phi I. The coefficient zi just goes along for the ride here. Notice then that your original quantity on the left is being broken into a series sum, and that the vector here that has the largest eigenvalue will be enhanced because of this lambda coming out front. Now, seeing that, you might like to try this again and again, and that's what's done. The matrix A might be applied a second time. You might think of that as A squared, and then a third time to get A cubed, and so on. I'll use S here, this superscript, to act as an exponent under the meaning that A squared means A times A, and then A cubed means A times A times A, and so on. All right, what's happening on the right side is that each time you do such a transformation, you kick out another product lambda I, and after doing S such iterations, you get lambda I to the S power. And so you can see that this particular term is going to dominate. We can put that in a better mathematical discussion by first saying that we're going to have well-ordered eigenvalues where this largest one is larger than the others, and each in turn is larger than the lower numbered eigenvalues. Then when we expand the right-hand summation, which is shown here, we take the large coefficient out of the last term here, and that coefficient is lambda sub n super s. It's really to the power s. To make up for that, we have to divide each of the other coefficients by that same term. And then you see that you get this ratio on each of the lower components, and because the number s grows as you iterate, you have this increasingly large exponent. What happens ultimately is that these terms here start dying out relative to this dominant term. You may have noticed that the participation coefficients play a fairly passive role in this derivation. If those are small or large, it really will be washed out in the end by the dominance of the growing value of that coefficient going as lambda n to the s power. So in the limit then, you're going to get that the vector that you have on the left side here, due to all these successive transformations, is going to approach the eigenvector corresponding to the largest eigenvalue. One side issue might be if this coefficient z sub n had been picked exactly 0, then you would have a problem, because except for round-off error, you couldn't converge to that one. So it's presumed that in your trial vector, you've exercised the physical coordinates in a way that gets some component or some part of the dominant eigenvector. Now, there will be a second vector that will be the most stubborn one to die out as you do the iteration. I call it the most stubborn unwanted eigenvector, and let's suppose in our case it would be phi n minus 1. That would be the eigenvector corresponding to the next to highest eigenvalue. Now, we're going to give an example here, say with 4 degrees of freedom, where we are converging on this eigenvalue and its corresponding eigenvector. But the next smaller eigenvalue is going to be trouble. It's dying off in the ratio of lambda n minus 1 to lambda n. That's the same in this picture as this ratio a over b. And you can see that that number might only be, say, 7/10. And so as you converge each cycle of your iteration, you will improve your answer by some 30%. The convergence of the power method apparently depends on a ratio of 2 distances. In the case of convergence to the highest eigenvalue, then you are comparing that value with the value of the most stubborn next largest eigenvalue. It turns out you can shift the origin that you are measuring these eigenvalues from and find a way to improve the ratio involved. That's called the shifting concept. So rather than use the original physical origin 0 here, let's propose to move the new origin to lie within this cluster of unwanted eigenvalues here. And when you do that, it turns out that you maximize the ratio of the distance out to the wanted eigenvalue compared with the largest distance to the most stubborn unwanted one. Here we have both of these equally stubborn in terms of their distance from the new origin. So what you've done then is to give a better ratio of distances and improve the convergence rate. It's not obvious that this trick works. In other words, you might think that if you change the origin of the eigenvalue, that it might somehow affect the physical problem, such as the eigenvector quantities and the directions the eigenvectors point in. But that does not turn out, and we'll look at the equations in the next figure to show that. The argument I've just given is rather geometrical and doesn't show the mathematics behind it. So now let's fill that in a little with some of the mathematics of this shift. Here was our physical problem in which lambda played a physical role. It was related to frequency, perhaps, such as the inverse of frequency squared, which is common as in the Stodola method, one of the versions of the power method. The vector u corresponds to physical displacements of the body. Now, when we decide to shift the eigenvalue, we'll name the new eigenvalue, capital lambda, as measured from the shift point, p. Mathematically, we just subtracted off this distance p from the physical eigenvalue to give you the shifted eigenvalue. Now, it still has the proper units and dimensions, but it's been shifted in space. If we put that into the original physical law, we now have, in the old physical eigenvalue spot, we have cap lambda plus p. Now p is presumed known, so we'll put it on the left side, and we take the product pu and put it as minus pu over here. Because matrix subtraction and multiplication is distributive, we can collect those terms together and come up with a new matrix here. It's kind of a general purpose matrix now. It's really a shifted matrix. And then we see the cap lambda plays the role of the eigenvalue in this new problem. So we're now going to iterate and find a solution to this problem, which in a sense has an artificial eigenvalue, but still has the proper eigenvectors. It does turn out that you converge to the same eigenvectors as before. So that in summary at the bottom I say that you do converge to these shifted eigenvalues that are related to the physical ones by the shift distance, and that the eigenvectors converge as they did before. Here I'll plot the shifted eigenvalues on the real number line. And now with the origin for the shifted eigenvalues shown as 0 here, we have the spectrum. Now, there has been no stretching here. It's only literally a shift of the origin. However, I do get negative values for cap lambda 1 and cap lambda 2. Our goal, of course, was to enhance the convergence to lambda 4. It turns out you can use shifting, though, for a second purpose other than fast convergence to the largest eigenvalue. You can also use a shift to get convergence to the smallest eigenvalue. And the way you would do that would be to shift your origin to where it lay in the center of the spectrum of unwanted eigenvalues. So I show this starred position again. This p distance I haven't shown back from the original physical origin. It would be some distance such as this. Now, if you look at the ratios, we know that there is a factor that attenuates the unwanted eigenvalues in the ratio A over B, and we see this time that that ratio is rather modest, again something like 0.6. So on each iteration we will get rather modest convergence to the lowest eigenvalue. It will come out with a negative number. However, when you recover the physical eigenvalue, it will be a positive eigenvalue. And interestingly, by optimizing here with this particular shift distance, we are going to have again two most stubborn eigenvalues, lambda 2 and lambda 4, dying out with this ratio of A over B to the S power. Let me make some comments about the power method. First of all, we've seen that it naturally converges to the largest eigenvalue. If we use shifting, we can improve the convergence to that large eigenvalue, or indeed by shifting somewhere to the higher frequency range, we can often get convergence to the smallest eigenvalue. So that gives us the eigenvalues that lie at the extremes of the eigenvalue spectrum, the smallest and the largest. Unfortunately, currently we don't have a way to get the interior eigenvalues, and shifting alone will not do that. We'll try to fix that up in our next section. You might note that there is either one or two most stubborn, unwanted eigenvalues and eigenvectors as you converge to the wanted solution. You might think of this as a contamination of the vector that you're iterating. Remember that, because that contamination is a special type, and we'll come back to that point later. To find the interior eigenvalues in the spectrum, we need to modify the power method even further. We'll do it by a method called sweeping. To discuss this, I'd like to number the eigenpairs in the order in which they are found. We'll still consider the special eigenvalue problem here in its nicest form, where A is real, symmetric, positive, definite. And suppose we've already found this eigenpair lambda 1 phi 1. If it was possible to write your trial vector such that the participation coefficient z1 was identically 0, then there would be no trace of the first eigenvector in this assumed trial vector. And in principle, then, you could do a power iteration and you would not enhance phi 1 because it would have no component whatsoever. It is possible to choose trial vectors that have no component of earlier vectors that have been found. In fact, this can be automated, and it was done by Hugh Flamenhoft you'll see a reference on the title page to that paper. Basically what you want to do is make your new trial vector here be perpendicular to the known first eigenvector. That's actually a single equation. It's the inner product of two vectors. When expanded, it looks like this equation. What it really is one equation in n unknowns. The unknowns are the components of the trial vector. The knowns, though, are the coefficients of the already found eigenvector. So it would be the amplitudes of each of the physical coordinates for the first eigenvector. You can actually solve then for one of the components in the trial vector, and let's arbitrarily take the first component, in terms of the other components of the trial vector. So this gives us some coefficients here that are determined by the first eigenvector. If you satisfy this equation then, which you might think of in the vector form above, you have the situation shown in the sketch at the right. The first eigenvector would be the blue line, and what you want to do is make your new assumed trial vector to be perpendicular to that blue line. Basically, you want it to lie in an n-1 dimensional subspace. Sometimes I call this a hyperplane because in an n-dimensional space, it's a plane-like surface, such as this, perpendicular to that line. Then what happens as you do your iterations is that your trial vector, as it's improved, will wander in this plane, but never will have a component lying along the original eigenvector direction shown in blue. The mathematics of the sweeping are carried out by forming a